So we will look at now two applications or three applications. One is reverse osmosis, second is gas separations, and third is uh, pervaporation. So let's start with reverse osmosis. We are going to look at these three applications very briefly, just the key principles and key factors that affect these operations. We are not going to do very detailed calculation and size of the membrane required and so on and so forth. All the principles that we have learned, just some key points or key concepts in these three applications. So if we start with reverse osmosis, what we are trying to do is to filter out water or to recover water and to reject the salt. So it might be seawater, it might be water having salt concentration at a low value. Just the concept of osmosis, just to refresh your memory, imagine that we have a salt solution here, imagine we have a water here. Water will try to go to this salt solution. That process is called as osmosis. If I apply pressure on this side to stop this water flow, the pressure at which this water flow is stopped is called as osmotic pressure. Right? If I apply pressure more than this osmotic pressure, water will actually go from the salt solution into the fresh water side. That's how we are able to recover water, remove water from salt solution, say seawater, and make water potable. So that's called as reverse osmosis. So this is called as osmosis, or sometimes, or very commonly, just because this is reverse osmosis, this normal osmosis is not called as normal osmosis, it's called as forward osmosis, as if this is some different osmosis. But just because this is called as reverse osmosis, then we give name here as forward osmosis. And pressure between these, water will still try to go through, but at of course lesser rate, because I am applying pressure here less than the osmotic pressure. That's called as pressure retarded forward osmosis. So we are not going to go into those details right now. We are only going to look at reverse osmosis, only key aspects of reverse osmosis. So of course osmotic pressure is decided by Van 't Hoff equations given by thermodynamics. You have seen that in your thermodynamics class. We are going to use Van 't Hoff equation, phi is equal to CRT, and sometimes this salt is going to dissociate. So take care of that. The total molality is going to be because of sodium ions as well as chloride ions. Sodium chloride is dissociating into two. So if I take 1 gram mole sodium chloride, I'm going to get 1 gram mole of sodium ions and 1 gram mole of chloride ions. Molality is going to be 2 times. It's not going to be linear all the time, so we are going to introduce a factor called as osmotic coefficient. Now, osmotic coefficient you can measure by instruments like vapor phase osmometry, and you will see that the osmotic coefficient changes with respect to the molality, and it is different for different components, and even some more salts here over a wider range of concentration. So osmotic pressure is actually lower than what is given by Van 't Hoff equation, or it can be more than what is given by the Van 't Hoff equation. So be careful. You will need to measure actually the osmotic coefficient and then only calculate the osmotic pressure. So right now we are only going to look at the sodium chloride. So we are going to go forward with this. Okay, so just some typical RO, if you read this paper in 1991, typical water recovery kind of applications, we want salt. So this is not ejection, this is rejection. So we want salt rejection of 99% and multivalent ion rejection. So any calcium ions that are there in seawater, magnesium ions that are there in seawater, divalent ions, we want a very large rejection of those. Typically seawater contains 3.53% NaCl. Brackish water, if you see, these are slightly less concentration, 0.2 to 0.58% of sodium chloride. What is plotted here is rejection versus flux. So you will see that we require a minimum 99.3% rejection for seawater application to make that water potable. And what this graph shows is what kind of flux we get from different kinds of membranes. So if you look at asymmetric membranes, you get very high flux. If you look at some of the older versions of these membranes, you get very low flux. And this is one more paper where they compared reverse osmosis to different applications. Again, cost is or economics in general is a function of time and space. but this one particular paper just gives you some idea. So if you're looking at 3% seawater, reverse osmosis costs are about the lowest in the lowest in terms of in terms of different applications. So if you take seawater, that's about 58 or it is 3% by weight. So that means it is 30 grams per liter. So seawater is somewhere here. So seawater here, you will have the multi-effect evaporation and reverse osmosis very much competing with each other. But electrodialysis and ion exchange would be very costly because of so many ions to be removed. Whereas if you take a brackish water, remember this was about 0.2 to 0.5% water. That means it is 2 to 5 grams per liter. So in that case, reverse osmosis is a very good option. Multiple effect evaporation is not such a good option because we have to evaporate large quantities of water. And of course, electrodialysis then starts coming into picture. That also can be very useful in terms of cost wise. We are not going to look at that. Ion exchange also is slightly expensive, but of course, with more and newer ion exchange media and very easy, it becomes a continuous. You can make it as a column operation, and these ion exchange resins can be having a very long life. So then it can even become more economically favorable. Um, just to give you some idea, so suppose we had seawater, we have 3% sodium chloride. We want to make a permeate, which is about 0.058% sodium chloride. And let's say reject, which is going back to sea, is about 8% sodium chloride. So osmotic pressure, if you calculate just by Van 't Hoff equation, it is about 26 bar for the feed, 0.43 bar for the permeate, and 69 bar for the reject. That means the feed we will have to pump to more than 69 bar. So typically 70, 75 bar, 80 bar, 100 bar in some old cases. Before we will be able to get only then we will be able to get a permeate stream. So this pumping of feed seawater from atmospheric pressure to as high pressures as 75-80 bar, that represents a significant pumping cost. So the permeate which comes out is at 1 atmosphere, but the reject coming out is at a high pressure. So this reject also is at high pressure. If you just directly discharge to the sea, you are wasting the energy associated with this reject stream or retented stream. And what you need to do is to make it economical, you need to use a pressure recovery pump or a combination of pressure recovery turbine. So essentially you are allowing the high pressure steam to be discharged to low pressure by way of turbine. You will recover electricity from that, and then that electricity, or you could have a direct mechanical coupling between a turbine and a pump, and you will use that to increase the pressure of the feed. That's so you are in effect utilizing the pressure associated with retentate. You are utilizing that to pump the feed from low pressure to high pressure. So the effective cost of compression is reduced. You will still need a small booster pump and electricity cost for that. But this is how you would tend to operate these commercial reverse osmosis plants, wherein we would recover and cost of water that we produce is at a premium. Just to give some quick calculation, let's say in a RO membrane, feed concentration is 1.88% at a pressure of 60 bar. Permeate is 0.058% at a pressure of 2 bar. Permeance, I am directly giving you, permeance of the membrane is 1.1 into 10 raised to minus 5 gram per centimeter square per bar, centimeter square per second per bar for water, and 16 into 10 raised to minus 8 meters per second for salt for this particular membrane. Look at the permeance values are in terms of different units, and we'll see that. What I would like you to calculate is the salt rejection, calculate the flux of water, calculate the flux of salt, calculate concentration polarization factor if Kl is 0.005 centimeters per second. So 5 into 10 raised to minus 5 meters per second. So if you look at the solution, again try to do this problem yourself based on what you have studied so far, then only go forward in the and in the presentation. Okay, salt rejection would be 1 minus permeate concentration divided by feed concentration. So that's 0.972. So it's not really a very good membrane. We won't be able to make potable water from that. In terms of the osmotic pressures of different streams, so 1.8 feed, 8% feed. So osmotic pressure is about 15 bar. 0.058% permeate stream. So osmotic pressure is 0.43 bar. This is again calculated from Van 't Hoff equation, not the actual value. The pressure that we had applied on the feed side was 60 bar and on the permeate side was 2 bar. So if you look at the water flux from permeance data, so this was the permeance multiplied by the delta P 60 minus 2 minus delta pi, the osmotic pressure driving force, delta P minus 15.5 minus 0.43. That's delta pi. So this is delta P minus delta pi. We had seen this earlier. So if you multiply, you will get 4.72 into 10 raised to minus 4 grams per centimeter square per second. If we convert this, this will come to about 17 kg per meter square per hour. We can even convert this into meter cube per meter square per second. That will be 4.72 meter cube per meter square second, or we can simply write it as meters per second. Salt flux, if we calculate, that's permeance multiplied by concentration difference. So 16 into 10 raised to minus 8, that's the permeance value that was given, multiplied by concentration. So 0.3 minus 0.00855. So that will give you the salt flux in terms of 4.8 into 10 raised to minus 8 kilomoles per meter square per second. So if you calculate the polarization modulus, e raised to jw is here, divided by kl is here. Take care of units. This is in terms of meters per second. This is in terms of centimeter per second. Divide this by 100. So you'll find that the polarization modulus Cm by Cb is about 1.1. Rejection coefficient you can take R 0.972. So you'll get this as 1.1. So hardly there is any polarization. That's because the flux is so small and mass transfer coefficient is very large. So if you use good turbulence promoter, you'll get large mass transfer coefficient. And flux is small because this has to be a very tight membrane. It's either porous, very narrow pore size, or sometimes it is also a dense membrane where only water permeates through this membrane. Okay. Very quickly, let's look at gas separation. Again, some principles associated with this. Gas separation we had seen in terms of Knudsen diffusion, if it was a porous membrane, or we had seen the diffusion mechanism. Look at the very second lecture, diffusion mechanism. We had looked at solution diffusion mechanism. Revise that and then go forward. Okay, so we had looked at solution diffusion mechanism. Flux was Henry's constant, diffusivity divided by membrane thickness divided by the partial pressure difference between the feed side and the permeate side. So we could write this in terms of permeability divided by the length. So this ratio is called as permeance divided by PIF minus PIP. So we could have any units of permeability. So flux, suppose it is in terms of kilomoles per meter square second. Partial pressure difference, suppose it is in terms of Pascal, SI unit if we take. Length in terms of meter if we take. Then SI unit of permeability would be kilomoles per meter square per second. This is meters, so it is multiplied. Partial pressure difference divided by, so it is kilomoles meter per meter square per second per Pascal. Now this is a SI unit, but units that are very commonly used are either we can convert this kilomole into centimeter cube at STP, because the kilomoles it will be very small flux, so we might want to represent that flux in terms of how much volume of the gas we would get at STP. Meters thickness we could represent in terms of centimeters. Flux per meter square we could write in terms of meter square per centimeter square. Second we could write in terms of second. Again there is a small correction. Let's see that. Right, so it is centimeter I have already taken into account, and this second it is per second actually. So take care of that. Right, and the partial pressure difference we could write in terms of any unit of pressure. So we could write this in terms of millimeters of mercury or centimeter of mercury. So this special unit that is used, is very commonly used in terms of gas separation, and we call this as 10 raised to minus 10 of this unit is called as 1 barer. So the permeability of gas in a membrane is represented in terms of the unit barer. Okay, so here's a small problem. Silica glass membrane, 2 micron thickness, separates hydrogen and carbon monoxide at 260 degrees centigrade. Let's say permeability of hydrogen is 200,000 bar. Partial pressure driving force is 1655 kilopascal. Permeability of carbon monoxide is 700 bar. Partial pressure difference is 550 kilopascal. Just calculate the flux of hydrogen and carbon monoxide through this membrane in terms of kilomoles per meter square per second. So basically it is an exercise in converting units. So bar is there, right? If you convert this driving force into centimeter of mercury and bar, you will get the flux in terms of centimeter cube per centimeter square per centimeter per second. In terms of, if you are multiplied by centimeter of mercury, so you will get flux in terms of centimeter cube at STP per centimeter square per second. You will have to convert that into kilomoles per meter square per second. So do that, do this exercise yourself, then only go forward. So if you want to see the answer, again it is from this. Hydrogen flux will be 0.055 kilomole per meter square per second. Carbon monoxide flux will be 6.5 into 10 raised to minus 5 kilomole per meter square per second. Okay, so if you look at different gas molecules, the permeability is related to their size. The bigger the molecule, smaller would be the permeability. So hydrogen, helium, they have high permeability, whereas big molecules like methane, nitrogen, oxygen, carbon dioxide, they have low permeability. Carbon dioxide, so it's not just based on molecular weight. So carbon dioxide molecular weight is 44. It is much larger as compared to methane, or much larger as compared to oxygen, nitrogen. But this is a linear molecule, whereas this is a tetrahedral molecule. Remember the carbon methane structure. So effective diameter of this methane molecule is larger than the linear molecule carbon dioxide. So carbon dioxide will diffuse faster than this methane. So it is essentially by size, but also the shape of the molecule has to be taken into account. Okay, so the polymeric membranes could be classified. These are, of course, membranes which allow the gas molecules to solubilize and then diffuse into across the membrane. So we could classify the polymeric materials into different categories. One, it could be based on their structure. So, for example, it could be a linear structure, or it could be a branched structure, polybutene if you like, or it could be a cross-linked structure. The polymers could also be thermoplastic, which means they soften with increase in temperature, but they are soluble in organics like polyethylene, or they could be thermosetting. They decompose at high temperature and they are not soluble in organics, like resins, phenol formaldehyde resin, for example. Polymers could be amorphous or crystalline. Amorphous means they are glassy in appearance, not crystalline. If you increase temperature, the transition occurs from an amorphous state into a rubbery state. This is called as a glass transition temperature. So they could be used as membranes below glass transition temperature or above glass transition temperature. In glassy state, they will have low diffusivity. In rubbery state, solutes will have high diffusivity. Or polymers could be crystalline. They would be opaque and crystalline in nature. With increase in temperature, the transition is to directly a molten state. So these molecules or these polymers would have to be used at temperatures below the melting point or below the, there's no such thing as glass transition, it is called as melting temperature. Just to give you some examples, you could have a cellulose triacetate, crystalline. In nature, melting point is 300, so it could be used below 300 degrees centigrade. Polyisoprene is rubbery, that means it is having a glass transition temperature, that is minus 70 degrees centigrade. So you could use it below minus 70 or plus 70 or above minus 70. Obviously, it will be used above minus 70 degrees centigrade in a rubbery state. You could have polyamide. Amide is the functional group, CONH. It would have a melting point, it's crystalline. It would have a melting temperature of 275. It has to be below this temperature. Polycarbonate. So carbonate is glassy. Glass transition temperature is 150 degrees centigrade. Amorphous. Polyimide, imide functional group. Polystyrene, again glassy, so it has a glass transition temperature of 74 to 100. polysulfone, sulfone group, right? PTFE, crystalline, it will be used below 327, that's the melting point. So different polymer structures are possible, and we could use different materials depending on what is the affinity of this material for particular molecules. Just to give you different factors, so if the membrane density goes down, membrane is less dense, that means there are more spaces for the molecules to diffuse, so permeability would be larger. Degree of crystallinity, if it goes down, the polymer is less rigid, it is flexible, permeability will go up. Degree of cross-linking, cross-linking is how different chains are linked to each other. If degree of cross-linking is reduced, then different chains can go away from each other, allowing the molecule to diffuse, permeability will be increased. Chemical affinity, if it is higher, obviously the permeability will be higher. So chemical affinity we are characterizing in terms of the sorption coefficient or in terms of Henry's constant, the solubility. Think about which of these effects would influence the Henry's constant or would influence the diffusivity. Think about that, pause the video before going forward. Okay, so the various membranes, just to tell you the different membranes here and different gases here. So look at different membranes, and if you look at the diffusivity, you can look at the diffusivity either as a row, diffusivity of different molecules. So hydrogen diffusivity is high, methane diffusivity is low, hydrogen diffusivity is high, methane diffusivity is low, hydrogen diffusivity is high, carbon dioxide diffusivity is low, oxygen nitrogen diffusivity is higher, carbon dioxide diffusivity is lower. So diffusivity is one parameter, and different membranes. So you can see different membranes will have different diffusivity, 0.47, 0.5, 1.5. So butyl rubber, rubbery state, whereas low density polyethylene. Or you can, so this is a diffusion effect. You can look at the solubility, Henry's constant. That is got to do with partitioning of how well different gases partition into the membrane. So for example, hydrogen, if you look at Henry's constant is 1.58. That means for a given partial pressure, a lot of it will get sorbed into the membrane or get partitioned into the membrane, whereas nitrogen would be very little, would have very little sorption. Or if you take for example polyvinyl chloride, hydrogen good solubility, methane very low solubility, right? Combined effect of diffusivity and solubility is given by this permeability, right? So now you can look at how the permeability changes for different molecules within a membrane, or for a given molecule how permeability changes with respect to different membranes, and we'll see an example slightly later. If you want to look at diffusion coefficient, again it is related to molecular weight. So higher the molecular weight, diffusivity will come down very dramatically. This is just diffusivity of different molecules in water, right? Whereas this is in different kinds of membranes, so silicon rubber membrane or natural rubber or polystyrene. You can see that diffusivity is very small. This is diffusivity into 10 raised to number. So it is 10 raised to minus 5, 10 raised to minus 6, 10 raised to minus 12, 10 raised to minus 14. Remember, 10 raised to minus 5 is like diffusivity in centimeters per second in liquids, and 10 raised to minus 14, you see 7 orders of magnitude or 9 orders of magnitude less diffusivity in the membrane. So this has to be experimentally measured. Sorption coefficient, again you can use Maury-Huggins theory. This is just a graph to show you that you can use thermodynamics to predict the solubility of different gases in membranes. So we are not in different polymers. We are not going to look at that. It's a part of advanced thermodynamics. We are not going to look at that. But just to tell you that you can predict solubility or Henry's constant from first principles. A little bit about separation factor. So if you take the feed side, let's say feed or retented side, we call the mole fractions by X. Permeate, let's say we denote the mole fractions by Y. Then we can write the separation factor alpha AB is Ya by Xa divided by Yb by Xb. Recall in liquid extraction we had defined separation factor when we had talked about the reaction and extraction simultaneously. So remember we had looked at separation of two different molecules, two different solutes based on their partitioning or based on their dissociation. When we had done dissociation extraction and liquid-liquid extraction simultaneously, we have defined separation factors. This is not like vapor-liquid equilibrium, where these relative volatility is defined as alpha and these are at equilibrium. This is not an equilibrium operation. It is just on the two sides of the membrane. Y is the permeate side, X is the feed or retentate side. Now, if I write flux for both components, so HA dA by LM divided by the partial pressure difference, flux for B, HB dB by LM and partial pressure difference. Okay. Now imagine some kind of membrane application. Let's say membrane is having a well mixed module. So feed side is well mixed, permeate side is well mixed. So we have a feed coming, part of the gas, some of the gases are going to the permeate side, partly A is going, partly B is going, and some of it is retained. It's a continuous operation, steady state. Both sides are well mixed. So if we say that both sides are well mixed, then the ratio here Ya by Yb will just be equal to the flux ratio Na by Nb, because it is well mixed. Whatever is coming, all of that will go away because it is well mixed. Okay, so Na by Nb I can write in terms of HAdA and the partial pressure difference, HBdB partial pressure difference. Right? I can combine these two. I can write the feed side in terms of XA and the pressure on the feed side, P1. I can write PA on the permeate side as mole fraction into the P2, into the pressure on the permeate side. Similarly, XB, similarly for the diffusion of B, we can write XB multiplied by P1 and we can write YB multiplied by P2. So if I say R is the ratio of pressures, P1 and P2 is the ratio of pressures. We want P2 to be lower, P1 to be higher. So it will permeate by way of partial pressure difference. A and B will permeate. So this factor, ideal separation factor, we will call it as HAdA divided by HBdB. Just like we had done maximum possible separation factor when we had done dissociation extraction. So this will just be the ratio of permeability of A and permeability of B. Now this expression I want you to simplify to keep only XA. So XB we can eliminate. XA plus XB would be equal to 1. YA plus YB would be equal to 1. And YA I want you to eliminate based on alpha A, alpha star AB. So you will find alpha AB. Do this for yourself. Make sure that you get this, then only go forward. So alpha AB, the separation factor, actual separation factor, is related to the ideal separation factor, the mole fraction on the feed side, and the pressure ratio and the separation factor at this particular condition. So alpha AB you will have to calculate iteratively. Alpha AB star we can calculate from first principles or based on diffusivity measurement and solubility measurement. So alpha AB star is a ideal separation factor. Depending on what XA is, you can calculate the separation factor by solving this expression. Okay, that's how this expression is useful. Let's take a simple problem for ideal separation. Let's say H2 and CH4 is to be separated using a microporous membrane with 1 micron active layer thickness, pore diameter 2 nanometer, epsilon 0.3, tau 1.5, tortuosity. If pressure is 10 bar, temperature is 100 degrees centigrade. I would like you to calculate the permeability and ideal separation factor based on, now this is a porous membrane, so solution diffusion. So remember Knudsen diffusion that we had calculated. So based on that principles, I would like you to calculate the ideal separation factor. Solve the problem yourself before going forward. Stop the video. Okay, so if you do that based on Knudsen diffusion, you will find permeability is hydrogen is 7.45, permeability for methane is 2.15, and alpha H2CH4. Just a small correction. This is not just alpha, this is alpha star. This is ideal separation factor, because it's just the ratio of the permeability. Now I want you to compare this for, let's say, if a dense PVC membrane was used instead, what would be the permeability and ideal separation factor? Okay, use data from the previous slides. Again, go back to the previous slide. So PVC membrane, right? So this is the PVC membrane. We have hydrogen separation from methane. So permeability is 1.3 into 10 raised to minus 13 and 0.021 into 10 raised to minus 13. Diffusivity and Henry's constant are there. Together is what is permeability. Okay, so if you go forward, for PVC, the ideal separation factor, again, small correction. This is alpha star. It is ideal separation factor. It is not alpha. It is not the separation factor at any value of any mole fraction. It is ideal separation. Ideal separation factor would be 1.3 divided by 0.021, 62. So look at this. 3.46 for a porous membrane has increased to 62 based on a non-porous dense PVC membrane. That's because the solubility and diffusivity both together come into picture. So it can give you a much higher separation factor. You would require much smaller area to get a purer hydrogen product from methane. And this is like a typical syngas kind of application where we want to separate out, make methane pure, or recover hydrogen from a reforming kind of application to go into a hydrogen fuel cell or hydrogen power car or something like that. Just another small problem. Calculate the ideal separation factor for, again, correction. This is alpha star, ideal separation factor. Right? So I would like you to calculate the ideal separation factor for oxygen nitrogen separation for air. So imagine you want to make oxygen pure. Let's say for medical application, somebody wants to be given oxygen for ventilation purposes and so on and so forth. Through different polymeric membranes, LDP, PMMA, PVC, butyl rubber. Again, use the data in the previous slide. So if you find, again, small correction, sorry about so many corrections, these are all alpha star values. Ideal separation factor because they are just based on the permeability ratio. Okay, so if you look at the data from the previous slides, LDP would have a separation factor, ideal separation factor of 3.01, PMMA 5.23, 3.82 for PVC, 4.02 for butyl rubber. And remember, we want to enrich oxygen. Suppose we had used porous membrane with Nernst diffusion controlling, then the selectivity or the separation factor would be just the ratio of molecular weights raised to power 0.5. So if I want separation between oxygen and nitrogen, the selectivity or the separation factor would be molecular weight of nitrogen divided by molecular weight of oxygen, whole thing raised to 0.5. So 28 divided by 32 raised to 0.5, which means separation factor would have been 0.935. So if it was a porous membrane, we would have permeated nitrogen. But because of solubility and diffusivity both together, oxygen is favorably permeated through the membrane. So we could enrich oxygen, which would not have been possible by porous membrane. So that's the advantage of using solution diffusion for gas separation applications. There is a very famous graph which is given by this paper by Robeson in 1991. He compiled data for different from different papers for oxygen nitrogen separation selectivity, if you like, versus the oxygen permeability in Barer. So this is like the selectivity and permeability trade-off that we were talking about. And in the 1980s, he found that no data of selectivity and permeability was beyond this line. Everything was below this line. In 1991, people have made more and more thinner and thinner membranes, more and more selective membranes. You could get a higher selectivity at the same permeability, or for the same selectivity, you could push the permeability to a higher value. And you can see that this is the 1991 limit. all data is below this. That means any membrane you take will always be on the left side of this graph. Okay, so this limit is the upper bound is called as Robison limit. And so the challenge, of course, is to make membrane more and more selective to oxygen. That means you want a polymer which will have very high affinity for oxygen but very low affinity for nitrogen, so that the selectivity is pushed up. At the same time, make a thin film composite, so make the membrane thinner and thinner, and push the permeability to a larger and larger value. So the idea would be to go to a high permeability and high selectivity membrane. That would be the target. So this is what is the data from literature for different authors and different investigations. Right. So this is where the future membrane research we should be conducting. Very quickly, in terms of pervaporation, so this is called as pervaporation. Reason being, it is called as perm selective evaporation. So what we are doing is so imagine this is the membrane, this is the feed side. Now the rate or flux is related to the partial pressure difference. So if I take a particular membrane, the partial pressure difference would be what will be governing the flux for permeation. So if I try to reduce this vapor pressure, if I try to reduce the if I try to increase the partial pressure difference, one way would be to increase the pressure. Another way would be to have a concentrated mass, which means we could have a liquid phase on one side. But if I have liquid phase on the other side as well, then the partial pressure difference would be very small. So way we would do is we would operate this vapor side on the other side of the membrane under vacuum at a pressure below the bubble point of below the bubble point of this mixture, so that on the other side, the permeate side, we would not have a liquid being present, we would have vapor being present. So the partial pressure difference now would be the vapor pressure on this side, and the partial pressure would be based on mole fraction and total pressure on the other side. So that's how we could increase the partial pressure difference and get a higher permeation. So if we could use it for separation of dilute organics from aqueous solution, then we would want a membrane which will permeate selectively the organic from the aqueous solution. So we would want a membrane which will be selectively permeable, or which would have affinity, which would have more sorption for the organic. Then we would want hydrophobic membranes. If you want to separate water from organic solvents, let's say we have organic solvent, let's say for example DMF, or let's say we have THF, tetrahydrofuran, we have let's say 1% water. We would want selectively water to go through. We would want membrane to be selectively having sorption for water. Then we would want a hydrophilic membrane. Some of the hydrophilic membranes are like polyacrylamide or polyvinyl alcohol or polymethyl methacrylate. Some of the hydrophobic membranes could be, say, PVC, for example, or polystyrene or PTFE, highly hydrophobic, or nylon, are very hydrophobic membranes. So flux now we would write in terms of the permeability divided by the thickness of the membrane. In terms of now the partial pressure difference would be xi pi sat and gamma I. Remember, it's a non-ideal solution. So thermodynamics, just like we had seen vapor liquid equilibrium. So this is on the feed side, and the permeate side would be pressure on the permeate side multiplied by mole fraction. Just to give you a problem, calculate, we have a liquid mixture, let's say ethanol and water. This separation is carried out at 60 degrees centigrade. Feed is at 1 atmosphere. So the feed is at liquid in the liquid form on the feed side, and feed is vaporized on the other side, the permeate side, through a PVA membrane. So PVA is hydrophilic, more affinity for water. Three situations are given. Let's say feed side we have 8% ethanol, permeate side we have 10% ethanol, weight percent. Feed side 36.4% ethanol, 23 weight percent ethanol. Third case 75% ethanol, 75.8% ethanol on feed side, 9% ethanol on the permeate side. the permeation flux, total permeation flux is given to you. Okay. I would like you to calculate the following. For some more data, at 60 degrees centigrade, vapor pressure of ethanol and water are 352 and 149 mmHg respectively. We can assume Van Laar model for the activity coefficient on the field side. I would like you to calculate the permeance of ethanol and water for first case, second case, third case. And then calculate separation factor for ethanol over water. So alpha ethanol divided by water for case 1, case 2 and case 3. This problem is not solved. You solve it on your own. Okay, so this is what I wanted to cover for this 3